Thank you very much for having me. And I think, yeah, I can start right away with the presentation. Also, thanks for the introduction of ConfigBox. Yes, Okan already mentioned, I'm presenting today video prediction and infilling with diffusion models. So this work is a little bit older. It's like, I think we published it like end of 2022, so it's like 1.5 years old. However, now with these new models coming out, like Sora and so on, I think it's somewhat still relevant. But first of all, diffusion is still used everywhere, right? It's still the generative model to go to if you have some generative problem. And video prediction, or actually video data itself, becomes more and more important since this model can now scale better and better and better. Also, there's just huge amount of video data. As we have huge amount of image data from the internet, we can also from YouTube scratch various amounts of video data, and we want to make use of that. Okay, so what we are focusing on is the problem of video prediction and infilling. So assume now you have a fixed video sequence. In this case here, this is an example of 6 frames, but you only know a few frames, like let's say the second and the 5th frame. And now you want to generate a video from this or predict a video from this given the 2 frames. So what you want in the end is basically a coherent video sequence, which makes, of course, physical sense, but also has like natural looks, let's say it like this. And this is the model which is able to do this must have strong predictive and generative capabilities. I mean, predictive makes sense, right? Because if I want to, for example, do video prediction, I somehow need to make some predictions within in the future. But we also need very strong generative capabilities because the future is multimodal. That means just imagine like you have a few frames of a car driving, and now you want to predict the next frames. I mean, there's a lot of things which can happen, but they all have the same likelihood. So you cannot just predict something, like you cannot just train the model autoregressive. You actually want to learn this multimodal distribution of the future. And that's why it's actually inherently a generative problem and not a regressive one. There are some models which just used simple regression for this, but they usually fail. They don't work as well. And that's why most people nowadays actually formulate it as a generative problem. So you can, in our case, since I mentioned we want to do prediction and infilling, we model it as a conditional generative problem. So we want to learn the probability of XU, where XU are the set of unknown frames given XC, so some set of known frames. And before our work, most common approaches relied on VAEs or GANs. So VAEs actually work very well, but we all know that they have this issue of blurry prediction. So they in terms of fidelity, they just don't produce as high fidelity videos or images as GANs. GANs, on the other hand, they produce very pretty pictures, but they extremely hard to train. And now if you want to scale everything up, this becomes more and more a problem. And this is the reason why we decided to actually use diffusion models for this problem. Okay, this slide I skip, I think. So when I say diffusion models, I use the word diffusion and score-based models kind of interchangeably here, because you can go from one interpretation to the other very easily. And I assume most of you already have heard of score-based models. I just want to, therefore, I just give really one slide as introduction. But the idea of a score-based model is basically, as it already says, to learn the score, because we can describe a process which is called the forward SDE, which brings our data to some kind of noise distribution, like a prior, so Gaussian distribution often used. And that forward SDE is also a so-called reverse SDE, which brings our Gaussian distribution back to our data distribution. And this reverse SDE is depending on the score. So if we could somehow learn the score, we can actually sample from our distribution without knowing the normalizing constant or anything. And the nice thing about this forward SDE is actually that, let's now assume, so we have here several noise steps, right? Which are, by the way, denoted as t. So if you wonder where t comes from, it's just the time step of your noise, or the scale of your noise. And if we want to sample from an intermediate step, we can actually sample from the conditionals right away. So we don't have to take an image or video in our case and run the entire forward SDE to get our training example. We actually can sample from the conditionals, so P of xt given xu in one step, which makes training very, very fast. And what you then basically do, just in practice, you sample t uniformly, sample the noise accordingly to it, get your noisy image or your noisy video, and then you try to predict the clean image. So this is kind of, you basically train it like an autoencoder, but this model, this unit, which you usually use, is then the conditional expectation of xu given xt, and that one is right away related to the score. So you can then plug that in to estimate the score, and then just use any your favorite SDE solver basically to run the reverse SDE. And you start with a noisy frame or noisy video, and you can sample your X0 basically, your data. The problem you might already see is that this reverse SDE, of course, needs several steps to solve. So solving this reverse SDE is actually quite expensive, meaning we need several forward passes through our model in order to arrive at our data distribution. And especially in videos, this actually becomes somewhat a big bottleneck. There has been a lot of work lately to speed up this process, like either using different like deterministic formulations or also distilling basically diffusion models in quicker sampling models. So there has been a lot of progress, but if you use the score-based model, you should still be aware of that bottleneck. They're still slower than VAEs or GANs because there you can just predict your data. On the other hand, of course, this iterative process called iterative refinement, of course, also gives you a lot of advantages in the sampling process if you want to do some kind of controlled sampling. Okay, so now we've talked about diffusion models, and what you could now do, we have a video data set, right? From, let's say we scratched it from YouTube or from somewhere and just train it. And then we hope in the end, when we want to do conditional generation, we can just take some known frames, put noise on all the other frames, which we don't know, which we treat as unknown frames, feed it through the model and hope it makes a nice video. But that doesn't happen if you train it unconditionally, because the model then does not does not harmonize the conditioned and predicted frames. So that's what you see here. I did train just a simple video diffusion model on something called moving MNest. So it's just two numbers moving randomly around on a black canvas. And then during test time, I conditioned on the first, I think, 5 frames and wanted to predict the next 5 frames. So what happens is now that our predicted frames, so the 2 zeros, which you see now, for our model, which at that time was just the go-to architecture for diffusion models. Nowadays, of course, people started to use transformers as they kind of take over pretty much everything. But the idea here was that in order to train the model just on the video right away as a normal diffusion model, we choose basically the number and position of conditional frames randomly. And then those frames we hold still, and we only diffuse the rest of the video. For example, in this example, I hope you can see it, it's a bit small, but at the top here, you can see, so we sampled 2, so that's the number of frames you condition on randomly from a uniform distribution. Then we chose the position on which these 2 conditional frames should be on, also randomly, between, of course, 1 and 6. So it then got 2 and 6. And these are the 2 frames we hold still. We do not anything with them, and we just denoise the rest. And then we feed that sequence, so this sequence of mixture of noisy and non-noisy images, towards the diffusion model. And in the end, the loss is only computed with respect to those images or frames, sorry, with respect to those frames which actually had noise on them. So we basically learn the conditional score given the known frames, which we choose randomly every time. And then first of all, through this kind of random masking later on, when we have a trained diffusion model, we can literally condition on every part of the video. So we cannot only do video prediction or infilling, we can really choose random frames we want to condition on and generate the rest of the video. And at the same time, as I mentioned earlier, we also still want to do unconditional generation, meaning just generating a video from scratch with any known frames prior. And for that, we introduced a so-called unconditional probability, PU. So that's just the probability with which we choose the set of conditional frames as the empty set. So we don't condition on everything. So let's say PU is 0.25. That means with 25% or 25% of the training steps, we do not condition on everything. So the model also learns the unconditional distribution.
Question here?
Yes. Yeah, sure.
Should I ask? Yeah, so I was wondering, is this something that you do during learning, or can you do it afterwards also?
Yeah, so this is what we do during learning, because if you would do this afterwards, then you end up here. So now let's assume you've trained your model completely unconditional, and then you just start sampling and you feed in that sequence, right? Like you have 2 known frames and you want to generate the rest. Then this happens what you see here. Like in this case, like on the 5 and 0, on these frames you conditioned and try to predict the rest, but it just doesn't harmonize. Like you still generate actually nice videos, but they don't at all harmonize with your previous example you conditioned on.
Okay, so you assume like you have this data set of like incomplete kind of videos or something like that. Or you remove some segments from.
Oh yeah, we remove, sorry for that. I think I should have clarified that earlier. So we assume that during training time, we have full data sets of all frames. So we assume during training time, the missing frames are basically known, so we can choose them randomly. And then only during test time, they're actually not known. Yeah.
So during training, actually, you need to make sure that the consistency holds. That's the ones where you removed, like that you're able to predict well and so on.
You mean now on the positions on what we want to predict, or?
Yes. So.
Oh no, that's why we use this randomization, right? That at each training step, the number and the positions of the frames you condition on is different. So it doesn't, that's why we basically learn the full conditional distribution, meaning we do not need any consistency between training and test time. So that means during test time, we really can do all kinds of problem solving, like prediction, infilling, and so on and so on.
I see. Thanks.
Yes. Okay. So I was maybe a bit quick with that. Yeah. Any more questions, maybe? Okay. Yeah, now going to the experiment section. So maybe let me very briefly talk about this FVD metric people usually use. As I already mentioned, the future is somewhat multimodal, so you cannot just compare your ground truth with your predicted frames in image space or in pixel space, because it doesn't make much sense, right? If your model predicts a realistic future, but that might be just slightly different from the ground truth, then you would still say it does actually predict something very meaningful. However, in pixel space, the MSE metric would actually be quite bad. So what people do is this FVD metrics, and that basically, very short, just means you compare the ground truth and your predicted frames in a latent space of a video action recognition model. So you just say that semantically, because we assume that in this latent space, we more have the semantics of the video and not really the actual pixel information. And we just say the semantics of the video should stay the same. But of course, in terms of pixel space, it can look very different. And yeah, so the first model we trained was on the so-called bear data set. It's just a robot arm moving around in a toy box and pushing objects randomly around. And we trained on a sequence of 20 frames. And the normal evaluation task here is to then condition on the first frame and predict the next 15 frames. And as you can see, we oh yeah, maybe, and one thing, these PU are the unconditional rates I talked about earlier. So we did experiments with several unconditional rates. And as you can see, we actually, in terms of FID, outperform all existing models at that time. And you can also see, which is somewhat interesting, that using some kind of unconditional rate actually helps even predictive tasks. So this is actually like at inference time, we now have a conditional distribution problem, right? We want to sample from the conditional distribution. But if we use some kind of unconditional training during training time, that actually helps the task here. And so the reviewer also wanted us to compare parameters, because to make sure that we just not scaled up and then we're better. And we can actually see that we use less parameters than most of the other models. So this diffusion, that shows just that this diffusion for video really works, and this is actually very powerful. So you can very easily like go from images to videos. And one more thing I want to say about this. So here, as you see on the left-hand side, we have the conditional frames, and on the right-hand side, we have the predicted frames from our round-bit model. But as I said, we used randomized masking, so we could also do a lot of other things. So we could also do infilling and so on and so on. But we don't compare that here because the typical comparison on this data frame, this data set, is simply prediction. But I will show you later examples that we can do all kinds of nice things with these models. But yeah, most evaluations were just on prediction, so we had to stick with that. We didn't want to retrain all the other models. And then, okay, going from the simple data set to a much more complicated one, which is the Kinetic 600 data set. It's a data set of, I think, 500,000 videos scratched from YouTube, like small videos with random actions from YouTube. And again, we trained the exact same, with the same parameters, just increase the model a bit, but otherwise the same parameters as on Bear. And the evaluation here is to condition the first 5 frames and then predict the next 11. And we can here see again that First of all, an unconditional weight helps even in the conditional setting. And we can see that, especially when it comes to fidelity, our model performs very, very well. Like here in the first frame, you see that we kind of have to predict how the fire evolves, which is very chaotic, right? Like you cannot predict actually how the next frame is supposed to look like. So you just have to generate somehow a meaningful, like a semantically meaningful sequence, which looks realistic. And our model does very, very well on these kind of tasks. Also in the last example, you can see water, which is also very well modeled by our model. And again, in terms of parameters, we actually use less parameters than the previous methods, at least the previous methods where we had access to the model and could check. And now, as I promised you earlier, so this is now the exact same model trained on kinetics, which I showed you here in this experiment. But as I mentioned, we can actually condition on a lot of things. We don't only have to do prediction at test time, we really can do infilling or upsampling. And the first example is infilling. So the first 2 frames and the last 2 frames are given. So these are here the static frames. And now we want to fill in the rest. So you can see, for example, here the ball goes into the, I don't know what it's called in English, but into the net basically. And then the last frames the model sees are where it already is out. So it now has to generate a meaningful sequence. And it does that actually very well. And also here in this last example, and that's actually my favorite one, you can see at the very beginning just the wave breaking. And the last frames is how the surfer gets out of this wave. And the model again has to make a coherent, or like fill this gap with a nice video. And it does that pretty well, I would say. It really models how the wave breaks and the surfer like slowly surfs out of it. Another example is just, for example, upsampling. So assume you have some frames given uniformly over your sequence. So in this case, 0, 5, 10, 15. Like very, very slow FPS rate, but you want to upsample it. And that's what we do here. So you can see. So these frames have a very big time gap in between them, right? And the model actually makes a nice video out of them in both examples.
So question here. So
yeah, sure.
You mentioned before that like what makes like this problem generative is the multimodality. So in your experiments, have you seen like some cases, interesting cases where this multimodality is clear? In the sense
oh yeah,
actually,
sorry, I think I forgot to mention that on this slide. So that's why I put in this example, right? If you see here the first frames, what you would expect is that the person just keeps on lifting his legs until it's what do you call it, handstand? Yeah. And we saw okay, I don't have the examples yet, but we saw in some examples that it actually does that because that's what it saw in the video data set. But here it actually kind of reverses the movement and it still looks very realistic. So it is able to model these two. Now, I have to admit here, you could also argue that this is like dangerously close to a failure case because sometimes in older video models, you just saw that in order to predict a realistically looking video, what the model sometimes did is just reversing the movements it had seen, right? So basically car driving forward and it just drives backward because it can literally copy the frames. So you could now argue that is also one of these cases, but since we have seen in the in some predictions that it actually does just predict the handstand, what it saw in the data set, we would now argue here this is actually very nice because we are able to model these two likely, I would say the two most likely outcomes. Yeah. But it is, of course, a bit tricky to find these examples in these data sets. Like maybe if you would, it would be maybe nice to actually predict something like this on oh yeah, actually here, sorry, yes, on bear, for example. In the paper, you can also see some examples where you condition on the first frame and then predict a lot of different outcomes. Because here, one frame does really not give you a lot of information because the robot like the arm movement is completely random. And it actually models that very well. I'm sorry, I did, like these frames look differently, right? Yeah, so I didn't put that in the slides, but if you check the paper, we actually have a section where we show that. We just condition on one frame and sample a couple of times, and all the sequences generated look actually quite different. Yeah.
Are there cases where maybe generate something quite nonsensical?
Yes, I will. I mean, I can already. So I will talk about that later a little bit. But yeah, okay. Yes. But remind me of the question if I miss it later. Okay. So yeah, and as I mentioned, we use this unconditional rate, right? Which seemed to improve prediction performance. Or also infilling performance. And so we were just interested in, can we also then just generate videos from scratch? So don't condition, you have no frames given, you just want to generate any video. And for that, we tested our models on the UCF 101 data set. And there's one thing I would mention before here. I would like to mention before here that this data set it's actually an action recognition data set. So it's quite small. It has, I think, 13,000 videos. And all these videos are really from different actions with different backgrounds. So there's no similarity between them, or not much similarity. So it's actually a very small data set for unconditional video generation. However, that's what people used as a benchmark. So we had to stick with it. And we saw a lot of overfitting and we're a bit concerned, but then we saw in most of the other models also this overfitting. So we would actually argue that this data set is not the best to show unconditional generation, but it's a benchmark. So we also tested on this. And we could see that at Runwit, we did not perform as good as the best gun model. So the best gun model is T-Gun version 2. And we were second in place. So still very good, but not as perfect. But here I also put in some newer work, video diffusion from Google. And there you can actually see that they perform very, very well on this data set. So it is not the diffusion, which is a problem. It was basically us. That's what I want to say here. So you can also, on these small data set, even with diffusion models, which sometimes are a bit prone to overfitting, but you can perform very well even on this data set. However, a takeaway message, of course, for me, also our model performs very well here, actually, even though it's a conditional and unconditional model trained at the same time. So this is a model where we can do this kind of unconditional generation and all the predictive tasks I've shown you before. Okay, and then limitations. So that's yeah. Then let's maybe talk about fast movement, because you talked about failure cases. So one of the biggest failure cases we actually saw is fast movement. So this is an example here where people dance. We conditioned, I think, on the first 3 frames, and then we see this jump is like the body just gets deformed very unrealistically. An interesting thing is, I think, that this is still, so it was a big problem as in previous models, but it still is somewhat a problem. Of course, models like Sora, which are trained on these huge data sets, do that much, much better. But if you, for example, sometimes look, especially at human movements, you can see some slide of small deformations of the hand. They're not as visible as here. Of course, our model is far worse than something like Sora. I don't even want to compare them. But I just mean this general problem of humans moving seems kind of difficult to model for these models. Another failure case or limitation is, of course, the sampling of long sequences, because since we use this 3D UNet, we feed in a fixed number of frames, and we cannot predict longer than that. So if, let's say, we train on 20 frames, we cannot, during sampling time, just sample out of the blue 25 frames. So you could do that, but then you have to go auto-regressively, meaning you have 5 frames given, you predict the next 10 frames. That's what your model can do. And then you take from the 10 frames you predicted, again, the last 5 and condition on those and make the new prediction, so auto-regressively. But of course, then you have this typical issue with auto-regressive models that your error amplifies, right? Because very likely in your first prediction, you already have some errors. Then you condition on those, also on those errors, and make a new prediction. And the error gets worse, 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 and worse over time. And this is a big limitation of these models. And actually, as far as I know, it's still a big limitation also with something like Sora, because also they are training on a fixed sequence length. So, or not, it's not fixed, but they have a limited sequence length. So, there's no paper to it. But as far as I know, they cannot just randomly predict as far in the future as they want. If they want to, they would also have to do it auto-regressively. So this is still a problem of these kind of models. If you don't train it auto-regressively, you cannot just generate infinitely long sequences. Exactly. And then maybe very briefly, because this is obviously now outdated, some future work at that time was, first of all, we want to reduce compute in sampling and in training. And for that, you could use something called latent diffusion models, which I guess also a lot of you are aware of. It's just you train a diffusion model as usual, but you do it in a latent space of a VAE or an autoencode or something. So you have a compressed dimension. And of course, then compute becomes, like training becomes much easier because you don't have to work on these huge video data sets. And the other possible future work is distilling the diffusion models in terms of sampling steps. So for the videos I've shown you now, we need like 500 to 1,000 sampling steps in order to solve the SDE, which is very, very expensive. People have already brought it down by a lot, but I think the most promising direction for that is distilling the diffusion model. So here, distilling doesn't mean distill in size, but distill in terms of how many sampling steps needed. So what maybe is a broad idea, what people usually do, with a trained diffusion model, you kind of generate a sequence, like the sequence of the ODE solver or SDE solver, sorry. And then what you do is you take a new model, which then tries to kind of make a prediction and skip the entire sequence. This is one way of distilling, and like one of the most famous ones is called consistency models, which kind of works as I just explained, and they can actually do 1- and 2-step sampling. They are not as good in terms of quality, but they are still like they come close and close. So if you're interested in some kind of real-time setting, then you should maybe go in those directions. Think of distilling with consistency models. And then last thing, I wanted to talk about two directions which I'm a bit excited about, and where I think video diffusion models can help a lot. Because with these models, we can, of course, do very nice things as generating pretty videos and so on. But there's actually much more to it. So one example I already mentioned is kind of autonomous driving, right? Like predicting basically how the car might drive, how the car might behave. But another one is for behavioral cloning in reinforcement learning and robotics, augmenting your test environment or your training environments. Because in behavioral cloning, we often have very limited data. So we have a fixed data set on which we want to train our robot, and then we want it to perform those tasks seen in the data set. But it's very hard to collect this data, so we have small data sets. And what we can do is maybe the data set is too small to train a completely new diffusion model on them, but what we can do, we can take a large pre-trained diffusion model and then augment just the videos. So here, this GenAug works with frames, but of course you can do that also with videos. So you have the task of put the mouse in the basket. So this is from your training set. But you now want to augment that so the your model becomes more robust. So you take that image, and now you so this is now a text conditional generative model. So you can of course easily include that also into the diffusion models. And then you change that in put the mouse in the box, but you change how the box looks like, or you add some new features on the table to kind of, again, make it more robust. Or you can even change the task, like here, put the waffle and maker in the tray. And of course, so again, this was done like with an image diffusion model. So you really have to augment frame by frame, which is very expensive. So you could also use a video diffusion model for that, which is probably more efficient and also produces maybe even more realistic videos because it's actually trained on a video. And another thing is these diffusion world models. I think one should be a bit careful with this term, what exactly means a world model. But again, in the offline RL setting, you often have a fixed data set, and then you want to train reinforcement learning on that. But another thing you could do is you train a diffusion model on that data set, but now you just don't augment the states. So that's what we see in the previous slide. But you actually learn a conditional diffusion model, like given so generating a state, action, reward, and the next state. So you then can you can generate new trajectories, completely new, and enhance your data set. But what you can also do is you can actually train an online RL method with that diffusion model. And I think that's kind of exciting. Of course, here you also have the issue is that diffusion models don't just what do you call it, generate like completely new sequences out of the blue, right? Like they also still in distribution. But what you can then do during training time, you can actually condition on high rewards and generate high reward sequences. So you can actually improve your agent. And there are several works out there. I just cited now 2 of them. I think there's even more out. And these are 2 kind of exciting directions where you can use diffusion or video models, or maybe let's use the more broad term like sequence diffusion models in order to enhance other methods like RL. Okay, thank you very much. Any questions?
Any questions?
Is there something else like?
Okay, thanks for your talk. So maybe I missed some training details. So I'm wondering if the missing mechanism of the training stage and test stage, if they are different, will your model work?
Again, sorry?
Like the training mechanism is different for training. The missing mechanism is different for training and testing.
The missing
stage.
mechanism?
Yeah, for example, if you train the model condition on like 10 frames, but in the test stage, you only have 3 frames to condition. with this model work?
Yeah, yes. So that's why like it's random, right? Like the number of, we never only condition on just a fixed number of frames. The number of frames is also chosen randomly. So if you have we always train on a video of 20 frames, we at each training step we choose a number between 1 and 20, and that is the number of conditional frames we use. So that's why yes, we could condition on any number of frames, like from literally 1 to 20. In that case, then yeah.
Okay, but if the frames is more than 20, so.
Oh yeah, so then you have this problem which I mentioned. Like we always have to stay in this. Wait, where is it? Yeah, here we always have to stay in this fixed domain, right? Like if you have more than 20 frames, then you have to start doing this autoregressive sampling, and then yes, you would have to chop it off and only condition on 10 of them. So kind of you disregard information you actually have, and that's an issue. Yes, yeah.
I also have a question, but a difficult one, so maybe others have question before. Okay. So yeah, I didn't know much about like diffusion models, so I was recently looking into them. It seems the first paper is like from 2015, and then
yes, exactly, yeah. Like that's but they use a slightly different formulation. Like they use this Markov model.
Yes.
So with discrete steps, but yeah, I think that's the first from I will press the author again.
Yeah, and then it seems it became more popular in the 2020 paper with this denoising
Yes.
version, which is basically not really like a contribution, but they kind of show this relation to score models, right? And then
yes, so that's one of the contributions. Another one is, as far as I remember, that in this forward process, in order to generate to get your training data, you don't you have this frame given, and now you want to get a noisy frame, right? You could run the entire Markov chain, or in this case, the SDE. But I think what they showed also is that you can sample from this right away. So you don't have to run the forward process, which speeds up training a little bit. Yeah.
okay, yeah, and then because they showed like good results, like compared to let's say GANs and so on, then it became very popular, right?
Yeah, that was in the second paper, I think, from that.
Yeah, 2020 onwards, there was like maybe this expansion, and already maybe we can say it's like a zoo of diffusion models, all sorts of variations. And I was wondering like how to categorize or how to think about these different variants. For instance, I've heard of like the ODE formulations, right? There's like rectified flows, and then there's always like SD-based formulations, and all sorts of, I think, maybe hybrids between these kind of models and like flows and so on, stuff like that.
Oh, okay, so the hybrids I'm not quite aware of, but
like,
yeah,
I saw already you mentioned the variation order-based method, right? Which is like doing the diffusion or in this latent space.
Yes.
Of like reduced dimensionality. It's kind of like using both like an autoencoder, which you could also use to sample from, right?
Yeah,
you have the variation formulation. So in that sense, it's like a hybrid.
Oh yeah, then it's a hybrid between a DAE and a diffusion model, exactly.
Yeah, exactly. And then these other flows, maybe they are, for instance, this like rectified flows and so on. Maybe I think they have connections to like other flows, maybe. I'm not really sure because yeah, I'm not super familiar with the literature, but yeah, how to kind of navigate in this environment, and what do you think pros and cons of different kinetic formulations are?
Okay, so but one thing about the rectified floats, I would be careful because I don't know them very well, so I don't think I can make any statements about that. But maybe to start, so between the ODE, the SDE formulation and the Markov chain formulation, there's really not much difference, I would argue. Like nowadays, I think still most people use actually DDPM for sampling, so this is a Markov chain formulation, but that's like there's really no difference. The bigger difference then becomes when you go to the deterministic sampling, which is the ODE formulation. So you can actually, from this reverse ODE, you can also derive a so-called probability flow ODE. And then you have a deterministic trajectory between your data distribution and your prior distribution. And those usually produce worse quality images, but they can sample faster. This is the first advantage. And the second advantage is, of course, you can do better latent space manipulations, because in the reverse SDE, or also if you use the Markov chain formulation, you always, at each sampling step, you add a little bit of noise. So if I start with the same noisy canvas, and I can actually generate, and I run my model twice, I actually get two different images. In the deterministic formulation, that's not the case. So for these kind of tasks, if you have like some kind of inverse problem task, you almost always use the ODE formulations. And there's also an equivalent deterministic Markov chain formulation, which is called DDIM. I'm not sure if you're aware of that. Actually, it's a nice paper, might be sweet. So you really have, you can think of DDPM and SDE. These are the two stochastic formulations. They are equivalent. And then you have, for each of them, you have a deterministic formulation, which is DDIM and ODE, or probability flow ODE, yeah. Then talking about flows and so on. So flow, for people who might not know it, like flow matching is basically a generalization of diffusion models. So in diffusion models, they really rely on connecting a Gaussian with your data distribution. But flow matching, they really, you can connect any kind of distributions. You can connect like a Poisson with your data, or you can actually even connect, people have shown that, two data distributions, which is other. So you sample from one data distribution, and then you just generate an image from the other one. However, as far as I've known, actually, when it really just comes to at least image generation, the diffusion models are still pretty much state of the art. I think only one of the really big ones used the flow latent lately, which is the latent from stable AI, I think the one. But in terms of, if you really just go for quality, then I think you should stick with diffusion models. Flows, I have not that much worked with them. They have this advantage that they are more general, right? Like a diffusion model is just a certain kind of flow, and a certain kind which just works very well and very easily. So yeah, that's how they are related. I don't know if that answers your question.
So much. That was very nice. And yeah, I was wondering, do you have any intuition why then the diffusion models kind of then generates higher quality images or videos compared to like other methods out there?
No, actually, so that question I cannot answer you, because I don't think that's even like really decided yet. So I would argue that from what I've seen so far, but I also know that people actually claim flows are the next thing. So that's what you should rely on. However, it's always a bit, again, like diffusion model is a flow, right? So yeah, I like why exactly the Gaussian works so well, I don't know. If it's really just tractability or something, I cannot answer the question.
Yeah, thanks so much. And finally, I was wondering about the network architecture. For instance, if you mentioned that people start looking into like transformers and so on, including there, right? What is the advantage there of including transform? For instance, is it able to pick out like a, let's say, some sort of sparse notion better? That's maybe because it has this capacity of being attacking, right?
Yeah.
So is there like a qualitative difference between using like transformer versus this UNet or etc.?
So you mean qualitative in terms of
that one can say, for instance, oh, it's better at capturing like physics reasoning or something.
No, I wouldn't go that far. So the transformer paper I had in mind was called DIT. Like I don't know if they wrote something about that specifically, but as far as I got their motivation, it was very simple. We know transformers are extremely, like through this attention mechanism, are extremely good at capturing kind of cross semantics, right? Like across a sequence, no, also with vision transformers across an image. And of course, also if you want to generate especially sequences, this actually becomes very important, right? If you want to do all kinds of infilling tasks. But I don't think they went that deep into the analysis of the transformer on actually saying, pinpointing that this is why a transformer is better than a UNet in this specific task.
I see.
So sorry, it's not really, I know it's not very satisfying answer, but I think that's okay.
Thanks, good. Yeah, thanks so much. Yeah. The questions or maybe questions from the audience? Do we have there? Yeah. Can you check?
So the question is, I don't know if you, I know you cannot, for the audience here, the question is if there's some kind of advantage of using the CLU over any other activation functions. And no, it's just slight performance. So we actually based our code base on another code base from OpenAI, so that was actually the paper you talked about, improved diffusion, which was the first diffusion model, which kind of showed that you can bring diffusion models like close to GANs. And so we used them, and they used CLUs. And when we used ReLU, it still everything worked, but it was just slightly better. So there's no pinpointing. It's really just engineering basically to improve the model.
Any other questions?
So yeah, thank you very much for listening.